All right, everybody. So welcome back. Now that we've met spherical coordinates, let's talk about some nice equations in spherical coordinates. So in particular, let's let c be a constant and see what happens when we hold some of the spherical coordinate variables fixed equal to a constant. The first of this would be probably rho. And this is, a really important point here. The equation rho equals to c represents a sphere. It's the equation of a sphere of radius c with center the origin, right? That's important here. So I'd say this is a pretty nice way to write the equation of a sphere, right? We had x squared plus y squared plus z squared equal to c squared in rectangular coordinates. And then in cylindrical coordinates, we could replace that with just r squared plus z squared equal to c squared, right? And that was a little bit better, but not much. And then spherical coordinates come in here and really save the day, right? Just rho equals to constant. That gets us this sphere on the nose, and that's just nice. So finally, a good equation for a sphere. This one's not going anywhere, so definitely learn it and love it, and yeah. All right, so let's see. What else can we do? Let's let phi, that angle of deviation from the positive z-axis, let's hold that one fixed and see what we get. So let's see. The equation phi equals to c, it will represent an upward opening cone when c is between 0 and pi over 2. So this one we chose here looks like it's probably about phi equals to maybe pi over 4, maybe, I don't know. So we have all the points in space whose angle of deviation from the positive z-axis is the angle of, say, this constant phi. Looks like pi over 4 to me, but, who knows? You let the thetas vary, right? And you let the radii, the rho, they vary as well. So that's why you extend out forever and you go all the way around. Okay, so, all right, so this one nice example. Remember this equation of this cone? Z equals to the square root of x squared plus y squared. Terrible equation in rectangular coordinates, right? But it was nice in cylindrical coordinates. If you recall, it was just z equals to r. That was pretty nice. Well, now we can get it even better. So we'll have z, that's rho cosine phi in spherical coordinates. And as we saw before, x squared plus y squared always simplifies to rho squared sine squared of phi. So we'll have rho cosine phi equals to the square root of the square of rho sine phi. So that can just simplify to rho cosine phi equals to rho sine of phi. And then cosine of phi, we can cancel our rho's if we are assuming rho is bigger than 0, I guess. Then, so we'll get cosine of phi equals to sine of phi. But what angle between 0 and pi over 2 has the cosine equals sine? Well, that's the angle pi over 4. So we're left here with the constant equation now. This cone is represented in spherical coordinates by the constant equation, phi equals to pi over 4. That's very nice. I think that's going to come into play when we start talking about some spherical boxes. We'll get to use cones and spheres as kind of two pieces that can kind of go in to make a spherical box. So let's not get too far ahead of ourselves, though. If we let that number, that constant c, be between pi over 2 and pi, we'd get a cone opening downward. So I don't know if I have a picture of that here. So let's just go back to this picture and see. If phi was between pi over 2 and pi, that cone would open, say, downward this way. Hopefully that's clear from this picture. I don't want to have to go to GeoGebra today. And I don't know how well GeoGebra plays with spherical coordinates. I think the verdict's still out on that one, or I could just be ignorant of how it works, or it just doesn't work. Okay, so the big takeaway from this is that spherical coordinates do work very well for integrating over regions that are bounded by either cones or spheres or both at the same time. So that's going to be big for us when we go to the next part of this talk where we actually do some integrals. So let's see. To just kind of finish it out, the equation phi equals to pi over 2. That's the one that's flat in the sort of middle here. That represents the xy plane, right? As then all the z coordinates are equal to rho cosine of pi over 2, but cosine of pi over 2 is 0, so all the z coordinates will be 0. And you can get all the xy plane by letting rho vary and by letting theta vary. So, okay, so that's kind of an interesting case in the middle where in between the cones that open upward and the cones that open downward, we have the flat xy plane. That's kind of an interesting way that these behave, these spherical coordinates. Okay, and then last but not least, we have the constant equations phi equals to 0 and phi equals to pi. And these represent respectively the positive z-axis for phi equals to 0 and the negative z-axis for phi equals to pi. Or if we let rho vary for not just non-negative rho, but if we let rho be negative as well, then these two equations would be the same thing. They just both give us the whole z-axis. Okay, so I think that's all we have to say about this. All right, one more thing now. A paraboloid. That was another surface that we saw at the end of 15.7 that we decided to try to describe with cylindrical coordinates. And I think it was pretty nice with cylindrical coordinates. It was a quadratic equation, something like z equals to r squared, I think. So let's take a look now and see how it fares in spherical coordinates. So we had z equals to x squared plus y squared. That was the equation of an upward opening paraboloid. And if we replace z with rho cosine of phi, and x squared plus y squared is again rho squared sine squared of phi, then I don't know, I guess we could divide out by rho, so as long as rho is not 0. And then we're left with the equation cosine of phi is rho times sine squared of phi. And so then I guess we could solve for rho, and we'd have rho equals cosine of phi divided by sine squared of phi. And so that is some kind of equation. It's an equation of rho equals to some function of phi, right? I like that. But I have to say that this is not the nicest equation, right? I'd probably rather deal with the cylindrical coordinate expression of z equals to r squared. But, you know, this is out there. So just one for the toolbox, I guess. So, okay, so how are we going to do some integrals? If we're going to do integrals in spherical coordinates, we first need to know what's the Jacobian matrix for this coordinate transformation. And we'll need the determinant of that matrix so that we can multiply our integrand every time we do an integral using spherical coordinates. So we have our coordinate transformation here. And remember how this Jacobian matrix works. You'll take, in the first row, you'll take the derivatives of x, the partial derivatives of x with respect to rho, phi, and theta. And then in the second row, we'll take the partial derivatives of y with respect to rho, phi, and theta. And last but not least, we'll do the same thing for z in the third row of the matrix. Or I guess here we could also say, take all these derivatives with respect to rho in the first column, or with respect to theta, or sorry, phi in the second column, and with respect to theta in the third column. So what does that give us here? Well, the derivative of x with respect to rho is just sine phi cosine theta. And the derivative of x with respect to phi is rho cosine phi cosine theta. And the derivative of x with respect to theta is negative rho sine phi sine theta. Okay, and then I'm not going to talk through every one of them. I think you can kind of see these are the derivatives of y with respect to rho and phi and theta. And in the last row here, we have the derivatives of z with respect to rho, phi, and theta. Notice there's no thetas here. So we get, or there's no thetas in the expression for z, so we get 0 for that entry of the Jacobian matrix. Okay, and I don't know what you know about determinants of 3x3 matrices. If you don't know about determinants of 3x3 matrices, just email me or consult Wikipedia or something like that. I'm sure they're not telling lies on Wikipedia about 3x3 matrices and their determinant. But in any case, if you do know about determinants of 3x3 matrices, then you won't have to consult me or anything else. But in any case, you can do a bonus homework to show that the determinant of this matrix is rho squared sine of phi. Notice how remarkably similar that is to x squared plus y squared. It's just kind of a tragic coincidence here. Rho squared sine of phi is this important quantity to remember when we're doing integrals using spherical coordinates. But rho squared sine squared of phi is something important just hanging around whenever you see x squared plus y squared. You can always convert it to spherical coordinates that way. Okay, so in any case, whenever we do a triple integral using spherical coordinates that is pulling back to this rho theta phi space, we're going to have to multiply our integrand by this Jacobian matrix determinant. And I know we're really supposed to multiply by the absolute value, but I promise you, with rho squared being there and with sine of phi being there, we should get these are both positive. I think phi varies between 0 and pi, wherein sine of phi is always non-negative, at least. So the absolute value of this expression is, in fact, just itself. So that'll be the term, this will be what we multiply all of our integrands by when we do spherical coordinate integrals. Okay, so I say this here that many of the examples we'll encounter will be over spherical boxes. There might be a couple that aren't, so be on the lookout. But the worst case scenario will be ones like this. Regions E of space that are given in spherical coordinates by the set of rho theta phi, where rho varies between the graph of two functions, g1 of phi, g2 of phi, and then phi and theta just vary between two pairs of constants. So, so that's the worst case scenario I think that we're likely to encounter in this class. But most of the nicest examples that we're going to encounter are over spherical boxes. And you'll be pleasantly surprised, I think, about how cool some spherical boxes look. So in this maybe most general case that we'll possibly see, if we have a function f of x, y, z defined over that region E, the triple integral of that function over E can be computed as follows. So we'll have our first integral will be this one with respect to rho, and the bounds are g1 of phi and g2 of phi. Our function will need to convert, so f of x, y, z becomes f of rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. That's x, y, and z in spherical coordinates. And then remember, we have to multiply our integrand by the Jacobian matrix determinant, rho squared sine of phi. And then this outer double integral is just over a box here because gamma, nu, alpha, and beta are all going to be constants. So I have it set up here to have the rho integral first, the phi integral second, and the theta integral last. But do note that by Fubini's theorem, you would be allowed to interchange these last two, phi and theta, because the bounds here are all just constants. Okay, so I think that's all we have for this part of the talk. So stay tuned for the next part of the talk where we'll actually do some integrals with spherical coordinates and look at some spherical boxes and maybe even some spherical non-boxes. So we'll see you then.